Okay, so this seminar is to cover the electronics part of O-level science syllabus. Since like as many students requested, they said that they find this area hard, so that's why I decided to do this part. So we'll see. I'm gonna cover the whole area of electronics as soon as possible because it's like so close to the examination. You don't have time to spend, like you don't have a lot of time to spend on this electronics part. So this will be a really fast session where I explain all the important facts as soon as possible. That is the plan for electronics. So let's start with electronics. So what is electronics and like why do we like what is the base of electronics if we talk about electronics? Base of electronics is as we all know it's semiconductors, right? It all starts with semiconductors. We found something called semiconductors and we then figure out that we can use these semiconductors to manipulate stuff. So use based on this concept we started working on semiconductors and then it developed up to the level of today where we can have a mobile phone which is really small and really thin but it can do a lot of stuff. So that's what happens with electronics. So it all started with semiconductors, basic giving a basic idea. We had conductors, things like metal, copper, very good conductors. They pass current electricity very quickly. Then we had insulators, which like maybe wood, things like wood, which doesn't allow any kind of a current flow through them. Then we found semiconductors, which have like properties which is related to both conductors and insulators. They are not insulators, they are not conductors, they are something in the middle. That is the idea of semiconductors. And if we talk about semiconductors, the first material that comes into our mind is silicon. You have heard terms like Silicon Valley kind of stuff. So when we talk about semiconductors, it's always about mainly about silicon. Silicon isn't the only semiconductor available, but it's mainly about silicon. So if we talk about how this thing like is established. So if we talk about how this thing is established, that's how this is how you see it. Okay, this is a silicon lattice structure. So you, as you know, in the like the last band, you have four electrons in every silicon atom, and they create bonds like this by completing their uh, like this band by completing this band by using the silicon next to the this one. Clear? So that is the basic idea. This is how they create bonds. Okay, that means they share electrons. Okay, they share electrons and they create a lattice structure like this. Okay, so this electron is from, so this is the silicon. If this is the silicon that I'm considering, this electron belongs to this silicon, this electron belongs to this silicon atom, this one belongs to this one, and this electron belongs to this one. And this guy provides this one, this guy provides this one, this guy provides this one, and this guy provides this one, and they create bonds and they create a very strong lattice structure like this. That is the basic idea. But actually it's not like this, it's a 3D structure. Okay, it's a very strong 3D lattice structure like this. See, it it actually looks like this. Okay, see, it's a 3D structure where each silicon shares one electron with each other. Clear? This is the actual structure. It's a 3D structure. Okay, it's a 3D structure. Now what happens in semiconductors? Okay, what happens in semiconductors is something like this. Due to the temperature, we know that these atoms and electrons are vibrating constantly. They are vibrating. So they have a very high energy, a very high kinetic energy. Due to this kinetic energy, some electrons tend to jump out of these bonds. Okay, some electrons tend to jump out of these bonds. Okay, so when they jump out of these bonds, what happens is it creates some free electrons. Is that clear? It creates some free electrons and holes. Clear? When they jump out of these holes, they create some free electrons and some holes. That is the basic idea. Okay. So when this happens, this is how it actually looks like in the bond. Due to high kinetic energy, some electrons come out of these bonds. Okay, see, they come out of these bonds. Now they have the ability to move freely. Okay, now these electrons have the ability to move freely. So there are two ways that these electrons can move. Okay, they can just swim through the system. Okay, just go through the system. Okay, they have that ability. These electrons can move like that, or else they can use holes to move from one electron to next one. That means something like this. When an electron, okay, when an electron releases like this, okay, now you have free electrons, and at the same time, when an electron come out of a bond, it creates a hole here, right? It creates a hole here. Now, when you provide a potential difference, or if you connect a battery to the system, due to that potential difference, electrons can move freely like this. Okay, electrons can freely move like this. Some electrons can freely move like this, and at the same time, electrons can use these holes to move. Okay, some of these electrons will freely move like this, and at the same time, some electrons will use these holes to move. That means this electron will decide, due to this potential difference, due to the battery, this electron will create a hole here and jump to this hole. Now you have a hole here. Then this electron will create a hole here and jump to this hole. Clear? This electron will create a hole here and jump to this hole, filling this hole. And this electron will jump to this hole. Likewise, now electrons have two methods of transporting. One is freely moving through the semiconductor, and the other main method is moving using the holes. Moving using the holes. It can use holes to jump through the circuit. So that means in a semiconductor, like in metals, maybe copper, take copper, only object or only thing which carries current in a copper wire is electrons. But when it comes to semiconductors, it's not only electrons, okay? It's not only electrons. We have electrons and holes. So electrons are moving in this direction, holes are moving in this direction. When an electron jump from here to here, hole come from here to here. When an electron jump from here to here, hole comes from here to here. Likewise, holes move in this direction and electrons move in this direction. So when we talk about a semiconductor, it has two methods of transporting electricity. They are using electrons by sending electrons in this direction and sending holes in this direction. That is the basic idea. Clear? That is the basic idea. That's the idea of a semiconductor. We call them intrinsic semiconductors. Okay, intrinsic semiconductors. Intrinsic semiconductors means actually like we use only silicon. We use only silicon. Like in this diagram, we use only silicon for intrinsic semiconductors. That's a different story. But sometimes the problem is when you consider natural silicon. When you consider natural silicon, the amount of free electrons are really low. Okay, you have a very small amount of free electrons when you talk about natural silicon. That means intrinsic semiconductors. But we need more electrons sometimes. To create more electrons, we use extrinsic semiconductors. Extrinsic semiconductors. So when we talk about extrinsic semiconductors, what we do is we take a silicon lattice and we mix some phosphorus. We mix some phosphorus. Why? In the last band, phosphorus have 5 electrons. in the last band, phosphorus have 5 electrons. So when and phosphorus when we enter some phosphorus into the silicon lattice, this phosphorus use 4 electrons to create bonds with other silicon atoms. But for the next electron, there's no place to go. Okay, when we talk about phosphorus, it has 5 electrons in the final band, so they will create bonds with each silicon atom. But okay, but it has 5 electrons, but only 4 can create bonds because it's in a silicon lattice. So this remaining electron will remain as a free electron. So each phosphorus atom brings one additional electron into the system. Clear? එක් phosphorus එකේනවා වැඩිපුර එක්කෙනෙක්ව system එකට ගේනවා වැඩිපුර ඉලෙක්ට්‍රෝනයක් පද්ධතියට ගේනවා. Clear? Each phosphorus atom brings one additional electron to the system. Clear? And when we talk about the other method here, so this process will create what? This process will create more electrons. It will bring more free electrons to the system, increasing the conductivity of the silicon. And at the same time, if we bring boron into the system, in the final band, last band, boron have only 3 electrons. So due to that reason, it creates 3 bonds with 3 silicon atoms, but to fill this hole, it doesn't have an electron. Clear? Boron has only 3. Okay? Boron have only 3. So this will remain as a hole. So for each boron atom we bring into the system, it creates an additional hole in the system. Clear? Yeah, අම්මතර සිදුරක් පද්ධතිය අරන් එනවා. It creates an additional hole in the system for each boron which we bring here. Clear? So that is the idea. So if we show it visually, what happens is something like this. We call this process doping. Adding phosphorus or boron into the system, we call it doping. So when we dope a system, what happens is we add some maybe when we add some phosphorus, maybe, yeah, see, it brings 4 electrons, but there's an additional electron that can freely move, which can't create bonds. See, which can't create bonds. So that is the story. When we bring a boron, see, there's an additional hole. There's an additional hole created here because it doesn't have more electrons to provide. Now, electrons can move using these holes like that. See, hole will keep moving in that direction because electrons move in this direction. Clear? That is the idea. Okay. So, that's the basic story about this one. So, when we add some boron and increase the number of holes, we call it a P-type semiconductor. When we add some phosphorus and increase the number of electrons, we call it an N-type semiconductor. Then what we do is we create a p-n junction. Okay, we create a p-n junction. That means we bring, as we know now, this p-type semiconductors has more holes. That means its majority conducting mechanism is holes. It has a lot of holes. Okay, no, very few electrons and lot of holes, free electrons and lot of holes. This one has a lot of free electrons, n-type semiconductors. Now what we do is we connect an n-type semiconductor and a p-type semiconductor. We connect them. Now as you know, p-type semiconductors have more holes, n-type semiconductors have more electrons. As we know, all the system everywhere in the nature, they try to neutralize. World like to neutralize. That means when you keep some water on top of a rock, it would flow downwards. It would flow downwards. Okay. Why? It need to reduce its potential energy. That's why, I mean, whole world is trying to, that's the nature of the nature. It tries to neutralize stuff. So when you have a higher potential, the river tries to go down and reduce the potential. So the natural systems are like this, like that. They like to neutralize stuff. So when these additional holes in p-type semiconductor are seen by additional electrons in n-type semiconductor, they try to neutralize with holes. How? They try to move like this, okay, and fill these holes. They try to move like this and fill these holes. Clear? Then they can neutralize. That means these electrons, they don't like to stay alone. Why? When they are alone, they are not that stable. When you are in a bond, they are stable. I mean, everything in world create bonds to be stable, right? We create bonds to be stable. Any atom, or like, okay. So here also what happens is they try to create bonds and neutralize things. So what happens is, now as you see, holes move in this direction, electrons move in this direction. Clear? Holes move in that direction and electrons move in this direction to neutralize. Okay. So now the problem is like this. Now it's not a problem actually. Now what happens is, okay, now what happens is, when you have a system like this, okay, uh, these holes are filled, I mean, here now you have current carriers, right? Who are the current carriers in this side? Electrons are the current carriers. They support current. In this side, these are holes are the current carriers. Okay. So when these electrons enter into this region, when these electrons enter into this region, we know that electrons are negatively charged, right? Electrons are negatively charged. And holes must be positively charged then, right? Why? When a hole and electron is together, it's neutral. Charge is zero. Then that means usually hole must be positive, electron must be negative. So not having an electron is something like positive, right? So we can consider holes are positively charged and electrons are negatively charged. So when electrons move in this direction and holes move in this direction, this side gains more negative charges, right? This side gains more negative charges. Why? These electrons move in this direction. These electrons keep moving into this side. That means this side gains more negative charges. And since this side loses electrons, that means its negative charges go away and positive charges enter to the system. So this side becomes positive. Little by little, this side becomes positive. And in this area, electrons and holes get together. Electrons and holes get together. And what happens is they become neutralized. Neutralized means now there's nothing to carry a charge here, nothing to carry charge here, nothing to carry charge here, nothing to carry here. See, all the charge carriers become neutralized in this region. Clear? They becomes neutralized in this region. Electrons fall into holes and they, I mean, when an electron is free, it can carry current. When a hole is free, it can support to carry current. But when an electron fall into hole, they become neutralized, then they are nothing. Okay? Then they are nothing. So here also this region, now this region have no charge carriers. It can't carry current, okay? It can't carry current. We call this region the depletion region, okay? This is the depletion region. High the Pradesh the depletion region, which doesn't allow any kind of a current through this area. Clear? It doesn't allow any kind of a current through this area. So we have a system like this now. We have holes in this side, we have electrons in this side, but here we have a depletion region which is positively charged in this side and negatively charged in this side, but and it doesn't have any kind of charge carriers because all the charge carriers it had are now neutralized. උදාසීන වෙලා ගිහින් ඉවර වෙලා තියෙනවා. So there are no charge carriers in this area now. So next, now this thing we call a diode, okay? This is what we call a diode. Now as we know, we have a positive region, I mean. Here we have positive, I mean holes. In this side we have negative electrons, but here we have nothing. We have nothing. That means there's a depletion region where no electrons and holes exist. And this part, it is negative now. Due to obtaining additional electrons, this side becomes negative. And as a result of obtaining additional holes, this side becomes positive. This side becomes positive. Now the problem is when one side is negative and other side is positive, now these electrons can't move in this direction and these holes can't move in this direction. Why? If this hole somehow try to enter into this depletion region, this positive, and as we know holes are positively charged, this positive region will repel it away. If this electron try to go through this depletion region, this negative charge will repel that electron away. Will repel that electron away. Why? Negative to negative repels, positive to positive repels, right? So now through this depletion region, okay, now through this depletion region, nothing can move. No electrons or holes can move through this depletion region. So we have an area, okay, where charges can't move. Now what can we do if we need to send a current through this one? What can we do if we need to send a current through this one? What sending a current, okay, through a PN junction, we call this a PN junction with a depletion region. We call it biasing. Biasing in the sense, now this region repels these holes and electrons away. Okay, if we can provide a very high positive charge to this side, a high positive charge to this side, and if we can provide a negative charge to this side, this positive charge, as we know, positive and positive repels each other. This positive charge will push these holes in this direction, and this negative charge will push these electrons in this direction. If we provide an enough charge in these two sides, if it is a enough potential, if we provide an enough potential, they will go through this barrier somehow. They will go through this barrier somehow, and they will start going through the circuit. They will start moving through the circuit. That is the idea. So we call this forward biasing. That means it will shrink this depletion region when you connect the battery such that this side becomes positive and this side becomes negative. This positive side will push these holes. This negative side will push these electrons and they will shrink this depletion region. They will somehow shrink this depletion region. Then electrons can freely move through the diode or this PN junction. Clear? See, now they can freely move. There's no depletion region. This thing we call forward biasing. For that, you have to connect the battery in correct direction. P side should be positive, N side should be negative. Then only electrons and holes can go through this depletion region. But if you do something like reverse biasing means we connect it in the opposite side. We connect it in the opposite side. That means you give a negative to this side, you provide a negative to this side, and positive to this side. Then what will happen? If you provide negative to this side and positive to this side, what would happen? Then these negative charges will pull these positively charged holes. This positive charge will pull these negatively charged electrons. So when they pull them away, this depletion region will increase. The depletion region will increase. There will be no current through the PN junction. So if you connect the battery like that, such that the positive side becomes that side and negative side becomes this side, then there will be no current through the circuit. See? So the idea is, okay, basic idea is through a PN junction, current can only flow in one direction. Okay? Current can flow in one direction only. Okay? When you forward bias, the current goes through this one, but if you reverse bias, current will not go through. But what is the magnitude of this battery that I should connect to make sure that current is passing through this circuit? It's usually around zero point 0.7. Why? As I said, in the formation of a PN junction, Negative charges accumulate here, positive charges accumulate here. They create a potential which is equal to around zero point 0.7 volt. They create a potential which is around zero point 0.7 volts. So there's a zero point 0.7 volt potential difference here. So if you need to send any current through this one, you have to shrink the depletion region. So to shrink the depletion region, you should at least provide zero point 0.7 volts. Clear? You should at least provide zero point 0.7 volts, something larger than zero point 0.7 or something larger than zero point 0.7. Then in that case, when you fill this zero point 0.7 volts, then current can flow. So there's a potential barrier in between. If you give an external potential which is larger than this potential barrier, and if you connect it in the right direction like this, you can make sure that current will flow through the circuit. So using this concept, using this PN junction concept, we have created something called the diode. We have created something called diode. Diode is a PN junction. Okay, this is a PN junction. This is a PN junction, and this is the symbol of a diode. This side becomes like this, and this side becomes like this. Then you have a diode. See, so we create an electronic equipment called the diode using this PN junction. And what is nice is through this PN junction, current can only flow through one direction. Current can't go in the other way. So this is a very important thing in electronics industry. By why there are a lot of scenarios. Okay, there's a lot of scenarios which you need to make sure that current can only go through in one direction. For an example, in my laptop, current should go in one direction. If current goes like this, if the direction changes due to some reason, my laptop may burn, my iPad may burn. So like that, in electronics, in many scenarios, we have to make sure that current is going only in one direction. So this is a very simple equipment which we created using semiconductors to make sure that when you connect this component into a circuit, it makes sure that current can go only in one direction, only in the proper direction. So if you connect a battery like this, such that this is the P side, this is the N side, such that P side is connected to the plus terminal and N side is connected to the minus terminal, then only current can flow through this circuit. Then only current can go through this circuit. If you flip the direction or if you change the direction, no current will go through this PN junction diode. Clear? You won't find any current going through this PN junction. That is the idea. So this is an equipment which is used to make sure that current will go only in one direction in my circuit. Clear? That is the basic idea of a junction diode. Okay. I mean, I'm just keeping this really fast because you can watch it in a very small time and like quickly cover whatever the thing that you need and move into other subjects. Okay, that's why I'm explaining this really fast. The next, rectification of alternating currents. Okay, one very important thing is rectification of alternating currents. That means in our grid we have current going like this. We have positive, negative, positive, negative. Our turbines produce a current like this. That means the current produced by our turbines, they change the direction time to time. Okay, they change the direction time to time. What we need is a nice current like this. Okay, our laptops, mobile phones, iPad, everything works like this with a current like this. So we have to somehow get the current provided by the grid like this. We get the current like this from our plug points at your house. You get a current like this. You have to somehow convert it into a current like this. Okay, so that process should happen. So how can we do that? How can we do that? There are two ways that we do that. One is half wave rectification, and another one is full wave rectification. अर्ध तरंग रुज करने सह पूर्ण तरंग रुज करने half wave rectification and full wave rectification. So the idea behind this rectification is like this. First of all, you have transformers. I have explained the functionality of transformers in my previous seminar, so you can watch that to see learn about transformers, and we did some questions too. So first of all, we get 230 volts, and if we need to reduce that. we use a step down transformer. For that, we can, as you know, we can reduce the potential, no, decrease the potential using transformers that we learned in last seminar. So this is a step down transformer where we can use to reduce the potential. Okay, this system can reduce the potential. Now we go adu karanava. Okay, from 330 volts to 3 volts. Okay, that is the first step, and we have to make sure, assume that this is your mobile phone. Assume that this is your mobile phone. You have to make sure that there is no negative current going through your mobile phone. Okay, you have to make sure that, otherwise your mobile phone will burn. For that, we use a very simple diode like this. Very simple diode like this. Now what happens? This side, this side provides an alternating current. Okay, this side provides an alternating current. That means a current which goes in positive direction and negative direction both. There's a current going like this here. There's a current moving like this. So in the positive half, current will try to move in this direction. That means this side will be positive, this side will be negative. So current will try to move in this direction. So what happens is, when this side becomes positive and this side becomes negative, diode allows current through the diode here. So what happens is, this positive half will transfer like this. The positive half will transfer like this. You can find the positive half going like that. It would pass through the diode here. It would pass through the diode. But what happens? Give me a second to adjust the focus. Nice. So now positive half will pass through the diode like that. Positive half can freely pass through the diode. Why? Diode allows current in that direction. Clear? So positive half will flow through the diode. So it will go like this and it will go through my mobile phone. But the when the negative half goes through the circuit, this side becomes, negative and this side becomes positive. Then what happens is, current tries to go in this direction. In the circuit, current tries to go in this direction. But the problem is, this diode, when this side is negative and this side is positive, diode doesn't allow any current through the diode. Why? It's a PN junction and it's reverse bias when you connect like this. So it won't allow any current in this direction. So you will not see any current going in this direction. So this negative cycle will not flow through the circuit. Negative cycle will not flow through the circuit. So it would be flat like that. Okay, it would be flat like that. Then again, next positive half will flow through the circuit, next negative half will not flow through the circuit, next positive half will flow through the circuit. Likewise, only positive half will go through the circuit. Then you will get a current like this through your mobile phone, clear, which is not that stable, which is not that good, but it doesn't have negative components. So luckily your mobile phone will not burn. Okay, your mobile phone will not burn. Why? Only positive current is going through your mobile phone. Clear? But there's a clear problem here, right? The whole negative part of the current is wasted. Whole negative part of the current is wasted. Okay? This negative part does not pass through the circuit. So this negative part, whatever the energy that we're going through the circuit, this negative part, this energy is wasted. Okay, this energy is wasted. That means our turbines use maybe diesel, maybe petrol, and they produce electricity, and then they send you a current, but you just waste half of the current. Okay, and that's not good. Okay, that's not good. This is not an efficient system. So if we can use this negative cycle also, it would be really wonderful. For that we use full wave rectification. Purna taranga Rujukarane. We use full wave rectification like this. This is a full wave rectification circuit here. This is a full wave rectification circuit. Now assume this is the symbol of an LED. Just assume that it's your mobile phone again. Assume that this is your mobile phone. Okay. Now again we provide a sine wave like this to our circuit. We provide a sine wave like this to our circuit. In the positive half cycle, okay, in the positive half cycle, this side becomes positive and this side becomes negative. That means current starts going like this. When current goes like this, now you should see current can't pass through a circuit like this. Why? Current can't go in this direction. Diode doesn't allow any current in this direction. Clear? Diode doesn't allow any current in this direction. So this current can pass through the circuit only in this direction. Only in this direction. Clear? Okay. Or else it would be really nice if I show it using my iPad. We'll see. In the positive half cycle, okay, in the positive half cycle, current will move like this, current will move like this, then it can't move in this direction, it can't move in this direction, it can't move in this direction. Why? The diode is reverse biased, so there will be no current in this direction, current will pass in this direction. So current goes through this circuit like this, current goes through this circuit like this. Clear? Then again, it have two options. It has two options. It can move in this direction or this direction, but again, it can't move in this direction. Why? Current can't move in this direction through a diode. So only choice is it has to move in that direction through the main circuit. Now it goes through my mobile phone. It goes through my mobile phone like this. Then it returns. Then it comes like this. Then it comes to the circuit. Then it goes through this part and returns to my network. Clear? Current goes in this path. It starts from the positive terminal, it goes in this direction and returns to my path. Now see, current moves in downward direction through my mobile phone. So that one passes like this. That one passes like this. Now my negative cycle, negative half cycle. What is the problem with the negative cycle? Problem with the negative cycle is okay. Problem with the negative cycle is in the negative cycle, this side becomes negative, this side becomes positive. This side becomes negative and this side becomes positive. Now the problem is now current, okay, now current can go in this direction only. Clear? Now what would happen is current will start moving in this direction. Why? Now this is the positive side. So current will move in this direction in this path. Now it has two options. It can go through this diode or this diode. But the problem is you can't go through a diode in this direction. Diodes only allow current in this direction. So your current will not flow in this direction. It will flow in this direction only. Then again it has two options. It can move in this direction or this direction. But again you can't move current in this direction. Why? Diode is forward biased in this direction. So you can't go in reverse biased direction. So your current will not pass through this circuit. It will go through this direction. And it will pass through the circuit. And it will return to the circuit like this. Then it would go through this path. Then it would return to the negative terminal. Now see, initially this side was positive and this side was negative. Now this side is negative and this side is positive. But whatever happens, current go through this circuit in the same direction. So the negative half cycle will also go in the same direction. Clear? Making sure that there's no energy wasted in the system. So this is a 100% efficient system. Why? All the current is passed through our circuit in the same direction, in the positive direction. Who started all this? Who started all this? This PN junction. Why? This PN junction allowed current only in one direction. PN junction didn't allow current in other direction. If you change the direction of the battery and if you try to change the direction of the current, current will not pass through this circuit. Why? These diodes, these PN junctions allow current only in one direction, and diode is just manufactured using a PN junction. See, we can do a lot of wonderful stuff using this very simple PN junction. Clear? That's what happens. But now there's a problem. Do you like your mobile phone having a current like this? It increases it. Yes, your mobile phone it will not blast. Why? You don't have positive and negative. It's always positive. It's not going to the negative side. But still it's not stable, right? Who need their mobile phone to go to fast charging, slow charging, fast charging, slow charging, fast charging, slow charging. You don't need your mobile phone to go like this, right? We need a stable charging pattern, right? If it is fast charging, mobile phone should fast charging. I mean, you can't increase the rate, decrease the rate, increase the rate, decrease the rate. It's not even good for your battery. So making this one directional is not enough for your mobile phone. It's not healthy for your mobile phone. So we need smoothing. Somehow from a current like this, we need to create something like this. We need to create something like this. For this, what we do is we use a capacitor. Okay, we use a capacitor. Capacitor means we connect a same circuit. This is a half wave rectification circuit. We connect a capacitor here with our mobile phone. Or in the next circuit, this is a full wave rectification circuit. With our mobile phone, we connect a capacitor.
Recording stopped.
Okay, so now what happens with this capacitor is, okay, what happens when you use this capacitor is something like this. Now the problem you see, our curve is like this, right? Our curve is like this in half wave rectification. Our curve is like that in full wave rectification. It increase and it decrease. Now what our capacitor does is, okay, in our positive cycle, okay, when our charge is high, when our current is high, it use some of this current, okay, it use some of this current and charge the circuit. That means when my current is high, it use some of this current and charge the circuit like this. Capacitors, the capacitor gets charged. Capacitor is something that we use to store charge, to store some charges, okay. So using this high current, when the current is higher, okay, when the current is around here, when it is higher, it charges itself using that current. Now when the current tries to reduce, it release its charges and create a current through the circuit. So it doesn't allow current to reduce like this. Okay, it makes sure that current is going through the circuit using the current that the charges it saved before. Clear? Then in the next loop it gets charged again. Then it release. It gets charged again. Then it released. So what actually happens is, okay. So what actually happens is, in the positive cycle, your capacitor gets charged. In this part, when the current is higher, your capacitor gets charged. It holds some charge here. Now when the current starts to drop, when the current starts to drops through this resistor, whatever the charge this capacitor stored, it send this charge through this resistor, making sure that current is not going down. So it makes sure that current doesn't decrease like this. It makes sure that it provides some current until the next wave returns. Until the next wave returns. and in the next wave it charges itself again. It charges in the next wave, it charges itself again. And when again the current tries to reduce, it makes sure that whatever using whatever the charge the capacitor stored here, it releases this charge and makes sure that the current will not go down like this. And in the next cycle, it charge itself again, then again release the charge. Likewise, it just try to make sure that previously it was like this. Now it makes sure that current doesn't go to zero. Somehow it managed to keep some kind of a value. Okay, that's the job of capacitor. When you have more, it's like maybe your bank account. Okay, when you have more money, you save some so that you can use them when you don't have money. Okay, when you have money, you store some charges, and your when your money goes down, you use your savings to, I mean, make sure that you can eat, drink, and stuff. Clear? It's like that. So this is like your bank account. Okay. When you have money, you store. When your money goes down, you use these savings to save your maybe your home. Clear? It's something like that. It's like your bank account. Same thing happens in full wave rectification. Okay. When it is higher, it saves some. When it is higher, it saves some charge, and when it goes down, it use whatever the charge stored in the capacitor, it release them and make sure that current doesn't go down. Okay. Then again it charges itself using the high current. Then make sure that current doesn't go to zero by releasing its charge. So again, it's like the bank account. When the current is higher, it stores some charge. Whatever the additional money you have, you store them. Then when the current goes down, you release them. Okay, so that you can live. Okay, that is the basic idea of a capacitor. Something that we use to store charge. Okay, it stores charge, and whenever the current is going down, it releases its charge and makes sure that current doesn't return to zero. Okay, so previously it was something like this, and my capacitor makes sure that the current is like this. My capacitor makes sure that my current goes like this. Here it doesn't go to zero. It's something like this. Okay, so that is the basic idea of rectification. Okay, sorry if my speed is high, but this is I'm doing this for you guys because definitely when you're watching these recordings, you won't have enough time to watch for like maybe 2-3 hours. So I'm gonna keep this really fast, okay? But I'm trying to explain things as much as possible, okay, in simpler terms, okay? Nice. So this is the idea, and also you have in your maybe in your mobile phones and all. You have things like this diodes connected to the circuit. Why? Assume okay, maybe your any device, your toy car, in your toy car, you can connect the battery in one side only, in one direction only. If you connect the battery in the wrong direction, your car will burn. Okay, the circuit in your car will burn. But nowadays it doesn't happen. Okay, why? We connect a small diode here. So if you correct the battery in your toy car, if you connect the battery in the correct direction, current will flow. But if you connect the current battery in wrong direction, it will not send the current in wrong direction through the circuit because we have connected the diode. So it makes sure that current will not pass through the circuit when you connect the battery in the wrong direction, which will save your toy car. Here, that is the basic idea. Okay. So we have like a very simple thing. Okay, diode is a very simple thing made out of semiconductors, but it has like hundreds of applications. Okay, really useful. Okay, thousands of applications you can find here. Okay, why pass current only in one direction, and there's thousands of places that we need to make sure that current goes only in one direction. Clear? This is another use case of this one. Clear? To save a circuit from like opposite current. And this, when we talk about these p-n junctions, okay, when you talk about this p-n junction, this is not the only use case. Okay, when we talk about p-n junctions, this is not the only use case. Okay, When you talk about PN junction, there are some other use cases like this. One is LEDs, light emitting diodes, and to be honest, these explanations are based on your syllabus. Okay, these are not the actual like 100% accurate. I mean explanations about electronics. Okay, even I'm doing electronics and telecommunication engineering in University of Maratua. So so I personally know that these explanations are not 100% accurate. It's just for the sake of our syllabus. If you choose to do science in A levels, you will learn more electronics. And if you somehow like me, if you somehow get selected to maybe University of Maratua to do electronics degree, then you will learn more about these things and you will learn about more applications. Okay, here we are learning the basics. In A level we learn something more advanced than this. Then in the university we will learn a lot of things related to electronics. It's a wonderful journey ahead if you maybe if you choose science. Okay, so anyways, first of all we have to go through all levels and we have to make sure that we are doing all levels, I mean, to the best possible extent. Clear? So let's first make sure that we are doing that. Okay, so this is an LED. LED is again a PN junction. Okay, to give a very brief description, LED is again a PN junction. Okay, it's again a PN junction diode. Okay, but what is nice is in LEDs they have made this PN junction in a specific way such that when an electron falls into a hole, when an electron falls into a hole, it releases some energy out. Okay, it releases some energy out when an electron falls into a hole. I mean, when an electron falls into a hole, it releases a specific energy like this. Okay, it releases an energy. So when it releases some energy out in LEDs, light emitting diodes, they have made these diodes in a specific way such that this energy is optical energy. So when this electron falls into this hole, it releases some optic energy, and that optical energy we use as light. That is the idea. So the LED is just a PN junction diode where it emits optical energy when electrons fall into the holes. So again, when you forward bias a diode, a light emitting diode, it allows current through the circuit. Then when current passes through the circuit, that means when electrons fall into holes, it emits light. That is LED. That is LED. Okay. So again, it is also a diode, but we do a small change. Okay. We do a small change. We put two arrows to show that this is not just a diode. This is a light emitting diode. That means when the current is passing through this circuit, it will emit light. So this is how you would see an LED. You have a length, I mean the length in two terminals are different. This is the anode, the longer terminal is the anode, the smaller terminal is the cathode, and the longer terminal, you have to connect the positive side of the battery to the shorter terminal, you have to connect the negative side of the battery. So this is how you connect a battery into this circuit. This is how you connect a battery into this circuit. You connect the positive side to the positive terminal and negative side to the negative terminal of the circuit. That's how you connect a battery to a circuit. Okay. So and you can see in this short side you can see a cut. I mean in this side, I mean side of the cathode, you can see a cut like this. If you look from top, you can see a cut like this. That is the shorter terminal. This side is the longer terminal. What you have to do is you have to make sure that you connect the positive side of the battery to this terminal and negative side of the battery to this terminal to make sure that this LED is working. Okay, to make sure that this LED is working. So this is what we call light emitting diode, LED. Then another application of PN junctions is solar cells. Okay, another application is solar cells. This is also a nice application, the solar cells. What happens in solar cells is something like this. Again, let's return to this one, a PN junction. Let's take a PN junction like this. Again, solar cell is a solar cell is a PN junction. Okay, solar cell is a PN junction. In a solar cell, what you have is something like this. This is the solar cell. You have your circuit. Maybe you have your home grid, or maybe a battery, or let's assume you have your household or your mobile phone here. Okay, this is a solar cell. Now what happens is you have a depletion region. Okay, you have a depletion region. What happens is in solar cells are made in a specific manner such that when solar energy falls into this region, when solar energy falls into this region, and you know that you have silicon here, right? You have silicon here. Although you don't have holes and electrons, you have silicon atoms here. That means this is a silicon lattice. You have silicon everywhere. Only issue is in this depletion region, you don't have free electrons or free holes. In this region, you don't have free electrons or free holes, but you have silicon everywhere. Okay, this is silicon, pure silicon everywhere. But this solar cells are made out of in a way that when optical energy falls into this area, using this optical energy, okay, using this optical energy, these electrons absorb some optical energy and then they come out of these holes. Then they returns out of these holes. Initially, this depletion region was made because holes were electrons fell into these holes, right? That's how this depletion region was formed. Electrons fell into these holes. Okay, that's how it was formed. But now, when you have free electrons and holes, okay, when you have free electrons and holes, what happens is, okay, when you have free electrons, when you have a depletion region like this, that means holes are filled with electrons. These solar cells are made in a way that using this solar energy, these electrons again can come out of these holes. Then again you can see free holes and free electrons are formed in this part. Now as you know, you have positive charge here, right? You have positive charge here and negative here. And due to this positive charge, this electron will be attracted in this direction. This electron will be attracted in this direction, and it will gain a kinetic energy and a velocity due to this positive charge, and it will move through the circuit like this, and it will charge your mobile phone and return to the circuit like this. Clear? That's what happens in a solar cell. When a solar energy falls here, it creates free electrons, and due to this positive and negative potential, this electron is accelerated and it goes through the circuit. Due to the acceleration, it gains some velocity and it goes through the circuit. It charge your mobile phone or something like that, or a battery, and it returns to the circuit. That's what happens in solar cells. Clear? That's what happens in solar cells. So solar cells is also again application of semiconductors. A very simple application of semiconductors. That's the idea. Then next topic we have to move into transistors. I hope you understood these concepts well. I kept it really fast so that I can make sure that you cover whatever required in a very short period of time. Okay, so what are these transistors? How do they work? So actually, when we talk about transistors, it is nothing new. Okay, that's nothing new. Like in transistors, it's just two p-n junctions. Okay, initially we learned something called diodes. Okay, we learned something called diodes, and in a diode, what we had was one p-n junction. Here we have two p-n junctions. But using these two p-n junctions, Like we can do lot of new stuff. I mean, as you know, in your maybe Apple M1 chip, you have millions of billions of transistors. So, like whatever the electronic systems you find everywhere, they are built out of transistors. But when we talk about what is a transistor, it is just a simple two PN junctions. That's all. Okay, that's all that you can find in a transistor. So, how do they work? First of all, we have two types of transistors. One is PNP transistors, other one is NPN transistors, and it's obvious now that you can understand the name. Here it's P junction and NP. Here it's N, P, and N. So what's in the middle? What's in the middle? It changes the behavior. So how do these transistors work? That is the critical part. How do they work? What is the behavior of a transistor? It's something like this. If I explain, this is how they make a transistor. You do them, then you have NPN junctions. Okay. Now, what you do is first of all we have to properly bias a transistor. I'll explain later. How do we bias a transistor? I'll explain it later. But when we properly bias a transistor, what happens is, as we know, as we know, if we come to explain this part, what happens is you have two PN junctions, right? This one and this one, two PN junctions. Then what happens is something like this. What happens is something like this. This is one PN junction and this is the other PN junction. What we do here is, if we properly bias this PN junction, okay? Now you know what is biasing. What is biasing? Giving positive to P junction and negative to N junction, right? So when you forget this part, this is just a single PN junction. Here, a single PN junction. Okay? When you properly bias this PN junction, okay? When you properly bias this PN junction, what happens is, there's a current going in this path. There's a current going in this path. And our objective is that since this base is really thin, we call this the base of the transistor. We call this the emitter, we call this the collector. When there's a current going through this path as a result of biasing this PN junction only, since this base is really thin, there are a lot of electrons will fall into this side. And so when there's a small current going in this circuit, a huge current will go through this circuit. So see, a small amount of current will go in this direction, a lot of electrons fall into this side. As a result of current going in this circuit, then this bulb will start to operate. That's what's happening in a transistor. Clear? That's what happens in a transistor. Since electrons go in this way, current goes in the opposite direction. So this is what happens. See, a very small amount of electrons go in this part, but a lot of electrons which come here, they fall into this side. That's what happens in a transistor. And this is how you see an actual transistor. Okay. This is the actual shape of a transistor. If you get a transistor from the market, you would see something like this. Clear? So I'll explain it properly. You can learn the symbols, okay? PNP, NPN, NPN. You have the this arrow in this direction. Here it's in this direction. Okay, you know this stuff. The important fact is how it works. So how it works means, to make it work, you need to properly bias the transistor. Okay, you need to properly bias the transistor. So biasing a transistor means is something like this. Let's talk about an NPN transistor. Okay, let's talk about an NPN transistor. NPN P, N. This is N, this is P, this is N. This is a separate PN junction, this is a separate PN junction. Now as you know, what happens is, there's a depletion region like this. There's a depletion region like this between this PN junction. There's a depletion region like this between this PN junction. So as we know, P side becomes negative in the junction. This side becomes negative, this side becomes positive, this side becomes again negative, this side becomes positive. So there's a depletion region formed like this. Okay, whenever you have a PN junction, you have a depletion region between them. There's another high pradesh P. Now what you do is, first of all, uh, this is the emitter, base, collector, and in N side you have more electrons, in P side you have more holes, in N side again you have more electrons. What we do is we forward bias this PN junction, this PN junction. How can you forward bias this PN junction? You connect the positive side of the battery to the P side, you connect the negative side of the battery to the N side. You forward bias this circuit. So when you forward bias this circuit, what happens is, okay, when you forward bias this circuit, what happens is, uh, current starts moving in this circuit. Clear? Current starts moving in this circuit. That's what happens. Clear? When you provide, I mean plus to P side and minus to N side, the depletion region here will vanish. Okay? The depletion region here will vanish. Depletion region will vanish. This depletion region will vanish and current will start moving in this circuit. Like this, current will start moving in this circuit. Like this. But actually you know that current is, when current moves in this direction, electrons goes in this direction, right? Can you remember this one? Electrons are something negative. So when something negative goes in this direction, that means current in this direction, right? We always mark the direction of positive charge. So when an electron moves in this direction, current goes in this direction, right? So actually current going in this direction means electrons are moving in this direction. So that means this negative part, this negative one, push these electrons away. So these electrons starts moving in this direction. Starts moving in this direction. Okay. This electron starts moving in this direction with the hope of going through this circle. Now when we are properly biasing a transistor, what we do is we reverse bias this PN junction. We reverse bias this PN junction. Reverse bias means we give negative to the P side and positive to the N side. Now we know that when we reverse bias a PN junction, what happens is its depletion region increase. Its depletion region increase. So what happens is when I reverse bias this PN junction, the depletion region increase. That means what happens here is this depletion region, it increase like this. It becomes a huge depletion region. And we all know that in a depletion region, N side is positive, P side is negative. So now what happens is when these electrons fall into this area, since this depletion region, you can see this side is negative and this side is positive. So since now these electrons fall into this base with the hope of going through this circuit. But when these electrons fall into this depletion region, now this minus charge push these electrons in this direction, and this positive charge, it attracts these electrons in this direction. So these electrons came here with the hope of moving in this direction, but lot of electrons are pushed in this direction. So now you can see there's a lot of electrons going in this path like this. That means there's a huge current in this circuit. So what happens is actually this one is the one who created the current. But now very small current goes through this circuit, very large current goes through this circuit. But who decides this very large current? This circuit decides this very large current because since this circuit is forward biased, he is the one who calls these electrons here. He is the one who calls these electrons to the base. And this one, what it does, it steals these electrons and push them this direction. Push them in this direction. So this is the control circuit. This is the circuit that is being controlled. That is being controlled. For an example, it's like this. This is like the tap. This is like the tap. This is like the emitter is like the water pipe. And collector is like the water outlet. Water outlet. Water is going in this direction. Water is going in this direction. Like this. But who decides the amount of water that goes through this circuit? This one. This one. Clear? This is the main circuit. Water flows in this direction. Lot of electrons go in this direction. But who decides how much electrons that will come here? Who decides that? It's decided by this circuit. So this is a controlling circuit. We are using a very small current in this path. We can control a very large current in another path. There's a very large current going in this direction, but it's controlled by the very small current going in this path. Why? He is the one who calls electrons. Clear? He is the one who calls electrons. So this is the transistor is a very simple concept where you use a small current to control a large current. Clear? That is the basic idea. So as a result, we have many applications of this. We have many applications of this. What are they? Now you should see using a smaller current, a huge current can be controlled. So when you change the smaller current in this path, this huge current will also change according to that pattern. Clear? When you change the small current in this path, the amount of electrons that come to this point will change when you change the current in this path. It will change this huge current. Clear? So using a very small current, we control a very large current like this. We rotate this tap. We rotate this tap. It decides how much water go through the pipe. So this is the main circuit. The main electron flow is in this direction, but this small circuit decides how much electrons flow in this circuit. So using this, we have come up with the main one of the main applications of transistors, that is the amplifier. Amplifier. Why? It's quite simple. See, it's quite simple. This is an NPN transistor. This is an NPN transistor. Whatever the current that goes through this circuit, it will amplify it in this circuit. It will be amplified in this circuit. Clear? So this is another method of biasing a circuit. You connect 3 volt from here to here and another large battery from here to here. I think these things in your syllabus, this is a huge area to be covered, but in syllabus, just knowing these things and remembering these things would be enough. But I'm just explaining things properly so that you have a nice understanding about what actually happens. But I think it's not required in your syllabus, so that I will briefly explain these things. So this is another way of biasing your circuit. You can connect two batteries like this and bias your circuit. And this is the base emitter circuit. This is the base emitter circuit. Okay. So there will be a small current going through this circuit. There will be a small current going through this circuit. And this is the main circuit. As I said, this is the main circuit. This is the main circuit. There will be a large current going through this circuit. But this large current going through this circuit is decided by this circuit. Clear? Is decided by this circuit. So you have a battery. When you switch on this, there will be a current going in this part. And due to that reason, there will be a current going in this part. That means if you actually try, if you turn on this switch, there will be a current going in this part. So this bulb will turn on. But this part there will be no current. Why? This bulb will be turned off. Why? This is open. And if you open this switch and close this switch, still there will be no current. Why? When there is no current in this part, there will be no current in the main part. As I explained before, current in this part decides how much current go through this part. So when there is no current in this part, there will be no current in this part even though you close this switch. But when you close both switches, now there's a current in this part, and since there's a current in this part, there will be a current in this part too. Clear? That's what happens. Okay. And whatever the current going through this path, it's amplified here by this large current is controlled by the smaller current going through this circuit. Clear? So this bulb, this bulb, the light of this bulb is weaker than this one. This will be a very strong light. Why? A lot of current goes through this path. If I explain you again using that video, what happens is in this circuit, we forward bias this one. We forward bias this circuit. So electron starts moving in this circuit, but lot of electrons fall into this area and they start moving in this direction to the collector. So who decides the current? See, there's a very small light in this bulb, but very huge light in this bulb. But who controls the light of this bulb? This part. This part turns on the switch. This part turns on the circuit. It calls electrons into this region, but now this collector steals all those electrons and there will be a huge current in this circuit. Clear? But who controls that? This circuit controls that. So this base emitter voltage decides how much current will go in this circuit. Then this current, this huge collector current is decided by this current, base current. Then this bulb will turn on. Clear? That is the basic idea. So here, using a small current flow, we decide a very large current flow. Using a small signal, you can control a very large signal. Clear? That is the behavior of a transistor. Just having a nice rough idea about this thing would be enough. Clear? So to make this bulb on, you need to turn on both switches. Okay, you need to turn on both switches. And if you need to reduce the light of this bulb, what you have to do is, who's the controlling guy here? Controlling circuit is this one, base emitter circuit. You have to increase the resistance in this path. It will reduce the current in this path. When it reduces the current in this path, it will eventually reduce the current in this path. Why? The current in this path is decided by the current in this path. This is the controlling circuit. This is the circuit that is being controlled. Clear? Is that clear? So this is a variable resistor. I think you know about these things. When you rotate these variable resistors, it changes the resistance among these pins. So when you connect a variable resistor to a point like this, it could change the resistance felt by this circuit. This is a simple amplification circuit. As I said, whatever the signal that goes in this circuit is amplified in this circuit. So you have a speaker here. You can connect your laptop here. These resistors, these batteries are to, as I said, properly bias the circuit. Why? Base emitter we have to forward bias, base collector we have to reverse bias. We have to do such stuff, right? I think you can remember now. Base emitter we forward bias and base collector we reverse bias. See, base emitter we reverse forward bias, base collector we reverse bias. To do that, there are different ways of doing that. So in these different circuits which are available in your notebook, these are different circuits made to do that. This is also here also this battery, this resistor is there, this battery is there to forward bias the circuit properly, to bias the circuit properly. Now you can connect your laptop here. It will provide a very small signal, but whatever the signal going in this path would be amplified and will be going through this path, right? Why? There's a very small charge flow in this circuit, but due to that charge, there will be a huge charge flow in this circuit, like shown in this video, right? So you can connect your laptop here. Due to the music that you play on Spotify, due to the music, the current in the current in this circuit will change. Current in this circuit will change due to the music that you play. Okay, the current in this circuit will change based on the music that you play. But due to that small current, there will be a huge current going through the main circuit. There will be a huge current going through the main circuit due to this small current, and this huge current can drive a speaker. So whatever the music playing on your laptop, you can send it to your speaker. That's what happens here. Clear? That's what happens here. See, this is your speaker. You can connect your small music or signal generator to this point. That signal generator will generate the pattern. Based on that pattern, there will be a huge current moving through this circuit in the same pattern, and it will turn on the speaker, and you will hear the same music in a very loudly. Clear? That is the signal amplification of a transistor. Signal amplification process of a transistor. Then again, we can use this as a switch also. How? How? As you know, first of all, this base emitter should be forward bias. When you forward bias this circuit, then only this circuit will turn on, as I explained. Okay, because if there's no current going through this circuit, if there's no current going in this circuit, these electrons will not fall into this part. If these electrons doesn't fall into this part, then the collector won't have any electrons to steal. Collector won't have any electrons to steal. So first of all, this circuit should work. For that, you should give that zero point 0.7 potential difference to this junction, right? As we know, any PN junction, to turn it on, you should provide zero point 0.7 potential difference. Can you remember? We learned that when we were learning diodes. Can you remember? We should provide zero point 0.7 potential difference to turn on this circuit. So when you provide zero point 0.7 potential difference to this circuit, then only this circuit will turn on, and then only this bulb will turn on. So based on that concept, you can use these transistors as a switch. You can adjust this value and make, when you adjust this one, and when this voltmeter value becomes zero point 0.7 or zero point 0.8, then this circuit is working, then only this bulb will turn on. But if you somehow adjust this resistor and reduce this voltage difference to something lower than 0.7, if you adjust this voltage difference to something lower than 0.7, what happens is this circuit will turn off. This circuit will turn off. Clear? When this circuit turns off, this circuit will not work. Clear? So what you can do here is, when you increase the resistance here, whatever the potential felt by this circuit will increase. So when the resistance here is zero, based on V equals IR, if R is zero, V is zero. So when you rotate this variable resistance, make it zero. Okay, when you make it zero, this voltage difference in this circuit will be zero. If when you adjust this voltage difference, the voltage difference will be zero. So when the voltage difference is zero, okay, when the voltage difference is zero, now what happens is, when the voltage difference is zero, this circuit will not work. This bulb is not working. Now you increase the resistance here. Which will eventually increase the voltage felt here. This voltage means this voltage, right? Why? This point is connected to this point, then this point is connected to this point. So whatever the voltage felt by this resistor is felt by this transistor, right? So when you increase this resistance, it will increase the voltage felt here. When you increase the voltage felt here will be increased. So when it passes zero point 0.7, all of a sudden this circuit starts working. Then this circuit will also start working, and there will be a current going through this transistor. There will be a current going through that transistor. That is the idea. So using this, you can do like wonderful innovations, something like this. Here it's an LDR, light dependent resistor. Assume that you need something. Assume that you need something. A bulb. You need a bulb. Okay, your garden bulbs. Consider your garden bulbs. You need your garden bulbs to turn on in night and turn off. I mean, in the daytime. So these LDRs are light dependent resistors. That means when light falls into these resistors, the resistance goes down. So you connect your garden bulb here. Now in the daytime, light falls into this LDR. When light falls onto this LDR, the resistance decrease. As we learned, V equals IR. When this resistance goes down, the voltage felt by this LDR goes down. So when the voltage felt by this LDR decreases, this end is equal to this end is connected to this end. When the voltage felt by this LDR decrease, the voltage felt by the transistor will also decrease. So when the voltage felt by the BE junction decrease and when it goes below zero point 0.7, there will be no current in this circuit. Clear? There will be no current in this circuit. Current will, so when there is no current in this circuit, there will be no current in the main circuit. So your bulb will not work. But in night, this light stops entering the light dependent resistor. So due to that reason, its resistance increase. When its resistance increase, the voltage fed by this LDR increase. Then the voltage fed by the transistor increase. Then this voltage pass zero point 0.7. When it pass zero point 0.7, current starts going through this circuit. As a result, current starts going through this circuit. Then this bulb will turn on. Clear? Then this bulb will turn on. Clear? That is the idea. So this is the simple structure of a garden bulb that works at night only. Clear how simple that is? Okay. These resistors, these batteries are there to bias the circuit properly. Okay. Now just read the practical and have a good idea about what is happening. But they are to adjust the circuit. Clear? Just having a nice idea about this thing would be enough. In A levels, we do all the calculations and decide these values. We do all the calculations in A level syllabus, but in O level syllabus, knowing what is happening and having a clarity about what is happening would be enough from my point of view. Clear? So that is the basic idea about electronics in your syllabus. So we learned about transistors, which can be used as amplifiers or as switches. Okay. So in this case, it acts as a switch. Okay. Here it acts as a switch, a nice switch. Why? Automatic switch, which turns off at like in the daytime, which turns on in the night time. A nice automatic switch here. So these are very simple questions. You can try these questions. You know that if it is a full wave, this is a full wave rectification. So what is the full wave rectification circuit? This is the proper full wave rectification circuit. But don't choose the answer with a capacitor. Why? If you had a capacitor, it would not go to zero. It would move smoothly like this. Okay. If you had a capacitor, it would move like this. It would not go to zero like this. So you don't have a capacitor here. So the answer should be this one. Here it's connected properly. This direction and this direction. Just see how the diagram is, how to draw the diagram properly, okay? Remember that part, okay? You connect two diodes like this. You connect diodes like this. Then this is, you connect these two like this. Then this like this. Then you have your, whatever the circuit here. Okay, just remember how to draw this thing properly. All the diodes are faced in this direction. Clear? and this point connected to the load. This point and this point is connected to the supply. Remember how to draw it properly. Another amplification circuit, you can try that one. This is also an amplification circuit, or a turn on off circuit. Uh, I mean, if I talk about this circuit, what happens here is name A, B, and C. A is the transistor, it is an NPN transistor. B are LEDs, light emitting diodes. C is a variable resistor. This is the symbol for a variable resistor. What is the change that you expect to happen in B1 and B2 in the circuit if S switch is closed and both LEDs are illuminated? When you turn on this switch, there will be a current going through this circuit, the base emitter circuit. So this will turn on. Since there's a current going through this base emitter circuit, there will be a current going through the main circuit too. If you turn on this switch and if you allow a current through this base emitter circuit, it will make sure that there will be a huge current in this circuit too. So when you turn on this switch, this bulb and this bulb both will turn on. Clear? Both bulbs will be turned on. Clear? If you turn on this switch. Clear? There will be a current going through this circuit. When there's a current through this circuit, there will be a current through the main circuit. That's how the transistors work. Clear? Which function? This is the function of a switch, right? In a way, this is the function of a switch. You switch on or off another circuit, but due to that one, another circuit turns on or off. So you can use this to demonstrate the switching ability in a transistor. But again, you can use this to demonstrate the amplification of a transistor. Why? As I said, the current going through this base is really small. So the light of this bulb will be really low. But due to that small current, there will be a huge current through the collector. So this bulb will be illuminated at a very huge, with a very huge luminous intensity. Okay, this light of this bulb will be huge. The light of this bulb will be small. So it can show that there's a small current in this part, there's a huge current in this part. That means it's amplified. Current is amplified. Clear? So that is the basic idea. Then they are telling that when the switch is open, B2 LED extinguishes. Explain the reason. It's obvious. When you turn on off this switch, the current going through the base emitter will become zero. When there is no current going in the base emitter, there will be no current in the collector emitter circuit. Why? That's how the transistor works, right? This is the tap. This is the tap. When you turn off the tap, there will be no water in the main pipeline. Okay, transistors, that's how they work. This is the tap where you rotate, but when you turn off, that means when you turn off this, no matter how much water available in the tank, no water will go through the transistor, because this is the controlling circuit. This is the circuit that is being controlled. So this is the basic idea about electronics. I just did a I explained everything at a very high rate, because I know that you don't have a lot of time to watch this recording now. But I think I covered most of the areas which are important. Okay. I would like, me being an electronic engineering guy, I would like to explain it more, but since the time doesn't permit, and since you don't have enough time, since it's really close to O levels, I'm just finishing it here, and just let me know if you need anything else, and like just try to go through and do some questions, and just don't be frightened about the examinations. Okay, just go and be relaxed and just go and write the exam properly. It's not a big deal. Just don't take it into your head and think about the examination too much. Just be comfortable with the theory points. If you are okay with the theory points, you will be okay with the examination. So that's all for electronics, and I wish you all the very best, and like for your examination. And I would like to see a lot of students in science stream after all of this. Thank you.